In this lesson, I will explore the classification of differential equations. In particular, we will learn in detail what a homogeneous differential equation is. Differential equations can broadly be classified into two categories: ordinary differential equations and partial differential equations. Ordinary differential equations involve derivatives with respect to a single independent variable, whereas partial differential equations involve partial derivatives with respect to multiple independent variables. Differential equations can also be classified based on linearity. A linear differential equation involves only the first power of the unknown function and its derivatives, while a nonlinear differential equation includes powers, products, or nonlinear functions of the unknown. For example, this is a linear differential equation. Note that both the function and its derivative appear linearly here. In contrast, this is a nonlinear differential equation due to the presence of products and powers of the function and its derivatives. Observe how the terms like y times second derivative and squared derivative make the equation nonlinear. Another classification is based on whether the equation is homogeneous or non-homogeneous. In homogeneous differential equation, every term depends on the dependent variable, like y, and its derivatives, and the equation is set equal to 0. Whereas in a non-homogeneous differential equation, the terms involving the dependent variable and its derivatives are set equal to a non-zero function, called a forcing function or source term. An ordinary differential equation of an arbitrary order is f of x, y prime, y double prime, and so on, equals 0, where y prime is the derivative of y with respect to x. Is said to be homogeneous, in general, if it is invariant under a scaling transformation, dilation, of the independent and dependent variables. X bar equals a to the power k times x, and y bar equals a to the power l times y. Where a is a positive parameter not identical with 1. K and l are any fixed numbers. The invariance means that the scaled equation looks exactly the same as the original. F of x bar, y bar prime, y bar double prime, and so on, equals 0. When we make this scaling transformation, there are two special types of homogeneous differential equations. These are uniform homogeneity and homogeneity by function. In uniform homogeneity, both variables scale uniformly, while in functional homogeneity, only the dependent variable scales. Let us consider an example of uniform homogeneity. The general form of this type of homogeneous differential equation is this form: dy/dx equals a function of y over x, is homogeneous of uniform type. Under scaling, both numerator and denominator scale equally, preserving the form of the equation. These are some examples of such differential equations. Now let's examine homogeneity by function. This includes linear differential equations with constant coefficients. Under appropriate transformations, the functional form remains invariant. Similarly, linear equations with variable coefficients also preserve homogeneity under functional transformations. Observe that when a function of x appears on the right-hand side of these differential equations, it becomes inhomogeneous. This is an example of a nonlinear homogeneous differential equation. If you found this video helpful, please give it a like, share it with others, and don't forget to subscribe for more content on mathematics and physics. Thanks for watching, and see you in the next one.